Is it okay?
Yes, it's okay. We can see it.
Okay, good. So I will present today some of recent progress on the real-time study of ultra-thin metal layers. So I am professor at the University of Poitiers, as you indicated, but before I forget, I would like to acknowledge my collaborator for this work. So people at the Institute, but also a close collaboration with Dr. Krause at Karlsruhe Institute Technology in Germany, and also with Kostas Sarakinos, which is now moved to the University of Helsinki in Finland. And also we are collaborating with the team of Success at Synchrotron Soleil, so headed by Andrea Alessandro Coati. And I would like also to acknowledge some of my former PhD students who contributed to the result that I will show today. So this is the context of my presentation. So we are interested in understanding of the early stages of growth of metallic thin films. This material, they are ubiquitous in many applications, starting from, for example, ohmic contact for the electrical properties, but also they are interesting for the optical properties, especially in low emissivity glazing. And also they are also interesting for their thermal properties. So these attributes are common to many metals. And also the last image I have shown here is related to the field of catalysis and plasmonics, where the formation of nanoparticle is particularly searched for. Unfortunately, for most metals growing on weakly interacting substrate, they manifest a three-dimensional morphology when you deposit them on silicon dioxide or other weakly interacting substrates. So they follow this typical scheme where you have the nucleation of islands, then they grow, and we have the coalescence and the formation of a continuous layer. So for some application, when it is required to obtain, for instance, ultra-thin continuous metallic layer for applications such as transparent conductive electrodes, so you need to get rid of this three-dimensional morphology. So there have been different strategies to move from a 3D to more two-dimensional mode. So you can act with the process parameter, you can play with the temperature and the flux. I will give some example later. But what is also very promising is to change the interface reactivity in terms of wetting properties. This is illustrated here. If you compare the growth of silver on silicon dioxide, so where you can recognize the formation of islands here, and the same film, which is deposited on amorphous germanium buffer layer, shows a continuous and smooth morphology. And the last strategy that can be employed is also to use additives. So they can act as surfactant, and they will modify the growth. So what is quite important in all this situation is to control the growth morphology, to tailor the desired physical properties in a way to optimize the device performance. And to achieve that, we have developed some real-time growth monitoring. So I will show you later the methodology. And the second example I will discuss today is related to silicides. So silicides, they are famous because they were used in the microelectronic industry. They were used as contact to make here the contact between the source and the drain in typical MOSFET transistor. And they are usually formed by solid state reaction between the deposited metal and the silicon substrate. And more recently, silicides, but also germanides, they have received increasing interest, this time for nanoscale devices, as illustrated here, where you have the use of silicides in nanowires. So it becomes critical to understand the phase transformation at the nanoscale. And what is also critical is to be able to capture what happened during the deposition of this metal on silicon before the solid state reaction. So for that, again, we will use some in situ and real-time diagnostics to monitor the early stages of metallic deposition on silicon and understand diffusion and interdiffusion effects. So this is the content of my presentation, I will present the research methodology, and then I will give you some results on these two topics on silver, mainly silver layer growth, and also the growth of the silicides and germanites. So the basic of our research methodology is that we are using several in situ diagnostics that are implemented in the high vacuum deposition chamber. So you have a sketch here of the deposition system equipped with different cathodes. This is a sputter deposition technique. And we have here illustrated the use of 3 different diagnostics. So the first one here, which uses a laser, is called the multiple optical stress sensor. So it's a curvature setup. It's a setup that is sensitive to the curvature evolution during deposition. We can also measure here the optical properties of the film that evolve during deposition. So we can use ellipsometry or surface reflectance spectroscopy. And we can also additionally use the electrical resistance setup, so in real time during deposition, in order to monitor the change of electrical resistance. So I will discuss today results relying on these 2 setups, the electrical resistance and the curvature setup. So how the curvature setup works. So we use here a system of laser beam. So we are collecting the reflection of laser spots on the camera here. And with changing the curvature of the substrate during deposition, we have a change of the lattice spacing, of the spot spacing, sorry. So from the relative change of spot spacing, we can have a direct access to the curvature here, kappa. And using Stoney equation from mechanical equilibrium, we can relate the curvature to the stress thickness product. So in the presentation that will follow, the stress is denoted by sigma here, and I will mainly plot here the stress time film thickness product. So typically what we can plot is the evolution of this quantity, the stress thickness product, as a function of film thickness during deposition. And we have most of the time non-monotonous response as illustrated here. So we have initially here a positive slope of the curve. That means tensile stress by convention, and then we could observe a change, compressive slope, compressive stress here due to the negative slope. What is also interesting is that we can capture with this technique what also happened after deposition. So when we stop the deposition, it's also possible to monitor the change of curvature, and in many cases we also observe some evolution after deposition. So this technique is interesting because it can be easily implemented in a vacuum chamber or in a system where you will make some annealing experiment. And it's also quite powerful because you can probe both crystalline and amorphous materials. The second technique that we have developed in the group is measurement of electrical resistance. So you can see here the schematic where you have the sample order. So the substrate is metallized on its edge here to make the contact. And then using this system implemented in the vacuum chamber, we are able to measure the variation of electrical resistance as a function of deposition time. So typically, if you look at the variation of the electrical response of metal that is grown on an insulating or highly resistive substrate, you have this typical curve. So you start from highly resistive value, and as the layer is growing, at some point you observe a fast drop here in the electrical resistance variation, and this fast drop is attributed to the percolation threshold. Percolation is the first electrical path that connect all the different parts of the layer and make the first conductive path. And from this typical curve, which I plotted here, I plotted here the resistivity, in fact, as a function of film thickness. You can also detect percolation, but also here at the minimum of the curve, you can also have information on the continuity thickness. That means the thickness at which the layer completely covers the substrate. And the last example that I will share with you is the the one that use a combination of these in-situ diagnostics at synchrotron facilities. So the idea here is to combine the curvature experiment that is shown here with information from X-ray diffraction and X-ray reflectivity. So by simultaneously measuring the curvature change, but also the diffraction signal and also the reflectivity signal, we can gain information on both crystal structure, morphology, typically the roughness, and we can relate that to the stress evolution. So I will start with some result on the growth of metallic layers. So I give you an example of 3 different systems: silver, copper, and palladium. So this layer, they are grown on what we call weakly interacting substrate, typically on oxides or graphene or amorphous carbon. So I start here with the evolution of the stress thickness product as a function of film thickness. So you have here the 3 curves for the 3 metals, and they both exhibit a similar stress evolution. So if we concentrate here on the green curve for copper, you can distinguish 3 regions. So the first one where the curve is slightly compressive here. So we have an initial stage where the stress is slightly compressive. Then you have an increase here. This corresponds to the tensile stress. We have a maximum, and then the system reverses back and we end up with some compressive regime. So this behavior is common to many metals growing in the Volmer-Weber growth mode. And this is related to the typical stages where you have first the nucleation of islands, isolated islands. These islands will grow in size and they will merge. And this constitutes the coalescence stage. And at some point, when the growth still proceeds here, we have completion of a continuous film and formation of polycrystalline film. So what is interesting to look at is the position of this tensile peak here, which gives information on the continuity. So this is an indicator very precisely where the deposited layer fully covers the substrate. So I call it the continuity thickness. So if you compare these 3 systems, I mean palladium, copper, and silver, what you can observe from this graph is a direct information on the continuity thickness, which is follow this trend, and it is in accordance with the adatom mobility, because palladium adatoms, they are less mobile than silver adatoms. So now I combine this stress evolution with the resistivity change. So for the same system here, the same color, you can notice that they have the same also electrical response as a function of deposition thickness. And from what I discussed before, it's possible to determine quite precisely here from this fast drop the percolation thickness. So this is the thickness at which the films becomes conductive. So by combining these 2 techniques, it is possible to obtain information on 2 relevant morphological transition thicknesses. First one is percolation thickness from the resistivity curve, and the second one is the continuity thickness from the curvature data in red here. And to give you here some support of this real-time diagnostic, we have extracted here plan view transmission electron microscopy images of 4 films, which are corresponding to these typical thicknesses here. And they illustrate that the growing film here, silver, follows the Volmer-Weber growth mode with islands, nucleation, and growth, and then the formation here of polycrystalline network. And the image 4, which is obtained just after the maximum here, correspond to the formation of a continuous layer. Then with this methodology in hand, we can probe the kinetics of the growth process. So we can look at the influence of deposition temperature. So this is illustrated here. So again, these are the stress thickness product evolution for silver at different temperature here, room temperature, and up to 413 Kelvin, and for different deposition flux. So in all cases, we observe again the same compressive behavior, but we can observe here a significant shift in the position of this maximum. So the take-home message here that you can easily observe is that when you increase the substrate temperature, you shift the thickness at which the film becomes continuous to larger film thicknesses. And we have also an influence on the slope, but I will not discuss here the issue of compressive stress in the steady state regime. If you now look at what is the influence of the deposition flux, so I compare here three curves at increasing deposition flux, low value to higher value. So by here a factor of 50 times higher, you can observe here that increasing the deposition flux shift the thickness at which the film becomes continuous to lower thickness value. In this case, this is related to the fact that increasing the deposition flux, you have a higher nucleation density, while if I go back to the previous slide, if I increase the substrate temperature, I have a lower nucleation density and the formation of larger islands. So now if I combine all these data and I plot that in terms of evolution of the continuity thickness as a function of inverse of flux, and on the right panel, it's the percolation thickness obtained from the electrical resistance measurement, again as a function of the inverse of flux. And for all the investigated temperature, in the log scale, we can obtain this linear behavior, which gives us some information on the underlying atomistic mechanism that govern the formation of the growth. And typically, we can extract here some information about the activation energy for diffusion, for instance. But what I want to point out here is that for the purpose of application, in order to obtain a continuous and transparent silver layer, we need to decrease the continuity thickness as much as possible. So with this strategy, by changing the temperature and flux, the optimal situation would be the following, which is obtained at 9 nanometer for significantly high deposition flux and low substrate temperature. But this represents kind of lower limit, and we want to push it further by applying another research strategy. So the idea is the use of additives, and I will concentrate today on the use of nitrogen addition during the growth of silver. So we are sputter deposited silver in a plasma that contains argon as a base plasma, but we will add some nitrogen in the plasma. So here is the result. I start to discuss the stress evolution. So the curve in black is the reference curve where we have discussed already. This is the reference curve for silver in the pure argon atmosphere. And then as soon as we increase here the nitrogen fraction in percentage in the plasma, then you can notice that the position of the tensile peak is shifted to lower value. And it's quite interesting here because starting from a reference value of 12 nanometer, we can decrease here roughly up to or roughly down to 7 nanometer. So this is a quite powerful method to obtain a more two-dimensional silver layer. And this is a proof of what happens by exploring the growth morphology. So these are plan view transmission electron microscopy images taken at different film thickness. So the film thickness is expressed here in terms of monolayer. So on the above panel, we have here the characteristic morphology for silver in pure argon. This is the reference film, and below we have the corresponding morphology for the growth of silver, in which we have incorporated 10% of nitrogen as partial pressure. So in the initial stage, it's hard to see some changes. So it's difficult to know if the presence of nitrogen will have an influence of the nucleation. But in the later stages, especially here where coalescence has started, so you can notice here we have already the formation of elongated islands due to the coalescence of islands. But in the presence of nitrogen at the same nominal thickness, we observe more elongated structure and more polycrystalline network. And the film will be also completely covering the substrate earlier. So this is a proof that nitrogen has an impact on the coalescence stage. And this is consistent with what has been also discussed by other group. And they propose that nitrogen could act as a surfactant and would also change the surface energy. So changing here the formation of crystal facets as supported by DFT calculation, you can see that absorption of nitrogen on some crystallographic surfaces decreases the surface energy. So this is one possibility, and we want to understand it in more detail. So I will not comment more on that. I will just inform you that we obtain similar result by incorporating also a small fraction of oxygen instead of nitrogen. But if you look at the properties of the film, if we compare the electrical resistance of the reference film here and the one that contain nitrogen in the plasma, you can see, okay, that we have shifted the continuity thickness significantly, but at the same time, we have here a higher electrical resistance, which is not desired for the applications. So what we have proposed is to selectively deploy the nitrogen at different stages. So in the schematic one, we have a continuous supply of nitrogen. In the second, we will deploy the nitrogen only for a short exposure time. And in the third scheme, we will introduce nitrogen after a certain delay. And the corresponding curve, they are here. So if we compare to the reference curve in black and the red curve as previously shown, the best situation is the one in blue, in which you expose the film to nitrogen in the early stages, and then you stop. So that means you modify the coalescence stage, but at some point here it's enough, and you continue the growth of silver in pure argon. So you can see that we have both decreased the continuity thickness without undermining the electrical performance. So this is the best solution to obtain at the same time a continuous transparent layer with the desired electrical properties. So in the remaining part, the 5 minutes, I will discuss some results we obtained during growth of palladium on a reactive surface, reactive by the fact that we have exposed amorphous silicon and amorphous germanium to palladium. And to illustrate this, it's nice to start with this curve where I compare in black the growth of palladium on weakly interacting substrates such as silicon dioxide. So this is the curve I have already discussed before, and we observe again the compressive, tensile, compressive behavior. So if you deposit the same palladium layer on amorphous silicon, this is the curve here in purple, where you can immediately notice a strong difference in the curvature, especially around 2 nanometer. We can detect here a characteristic tensile peak, which was not present for the case of palladium grown on native oxides. So I just remind you that this curve is typical of Vollmer-Weber, where you grow isolated islands in 3D. And this curve is more complex, obviously. We have to explain this part. And then for later stages, it looks like we have similar trend with this one. So what is also striking is if I now compare the stress response for palladium on silicon and germanium. So they are a striking similarity in terms of stress response, especially here, the formation of a peak here around 2 nanometer. And if you look now at ex situ characterization of the palladium layer, these are reciprocal space map diffraction pattern of the palladium on germanium and palladium on silicon. They are also showing similarity, and especially we have here the spot corresponding to the FCC growth of palladium with very narrow texture. And we have also here some rings that correspond to the formation of silicides and germanide compounds. So these compounds, I will show you in the next slide, they were formed during deposition at the interface. So how we could come to this conclusion is by combining several techniques. So again, I start here with the curvature I've discussed before, and then I superimpose these to the XRD, X-ray diffraction pattern, and X-ray reflectivity data. So from the X-ray diffraction pattern, it's possible to follow the structure evolution. So if we start from the deposition of silicon, this is an amorphous layer and there is no diffractive signal. It's close to the background. And when we start depositing the metal here, you can notice that initially there is no intensity change, and at some specific here thickness, we observe here an intensity increase, which is related to the crystallization of this palladium to silicon. So we have here a proof that the tensile peak that was observed by curvature is in fact related to the crystallization of an interfacial compound, which is the palladium to silicon. And then as the growth continues, we have the formation of palladium crystals, which are epitaxially grown on this silicide. So with the reflectivity is also complementary in a sense that we could observe and change in the period of these fringes, which is related to the different density between the silicide and the metal layer. And at the end, when the palladium starts growing, we can observe here a decrease in the magnitude of these fringes, which is related to the formation of a rough surface. So we can gain information also on surface morphology by combining all these techniques. So these are some conclusions I want to share with you, though, that the in situ and real-time monitoring that we have developed over the last years, they are quite powerful in order to provide some key information on gross kinetics, obviously, but also it's very sensitive to interface reaction and phase formation. So they are well suited to study nanoscale systems. By combining the stress evolution with X-ray diffraction at synchrotron facilities, it's possible to understand the interplay between that. And this is also interesting for solid state reaction. And the approach offers also some design route to obtain tolerable layer morphology, and also to optimize the growth process to obtain the desired properties. So I have shown you before one example for the case of silver, where we could modify the thickness at which the film becomes continuous at the same time without undermining the electrical resistance. And we have currently an ongoing project in order this time to understand in more detail the morphology of silver islands. And for that, we are combining this grazing incident small angle X-ray scattering technique with the diffraction and the curvature. So thank you for your attention. And if you have some question, I would be happy to answer.
Thank you, Dr. Gregory Abedini. Let me see, we have a question. Yes, we have a question here. Should I read it or?
Oh, I see it in the chat now. Okay, and the question is mixing different things. So the first one is the effects of post-growth treatments. So typically, yes, we have to ensure that the layers are stable. So they should be stable against oxidation or against annealing, where typically we can have an increase of grain size. And the second part of the questions, it's a bit strange to me because it's connected to another field. So I don't see the link with the field electron emission of diamonds. Without further information, it's difficult for me to address the second part of the question. Sorry.
Thank you for your great presentation. And I think another question is here.
Oh, okay, I can answer this one. So typically what we are targeting now is the development of silver as a transparent conductive electrode for flexible electronics. So the idea is to replace indium tin oxide, which is the material which is used, which is brittle, with some